In this video, we are going to have proof of two theorems. The first one gives the criterion for any homomorphism to be an isomorphism, and then the second one is first isomorphism theorem or fundamental theorem on homomorphism. Now we first see the criterion for a homomorphism phi of G into G bar with kernel K phi to be an isomorphism, and that is nothing but the kernel phi should be singleton E. That is the necessary and sufficient condition for phi to be, which is a homomorphism from G to G bar, is an isomorphism if and only if kernel phi is singleton E. Now first what is given we write, let phi from G to G bar to be the given homomorphism with kernel K phi. Now for the first part we'll assume that kernel phi to be singleton E, and we'll prove that phi is 1 to 1. So for that we'll have to consider the images to be equal. So let phi of x be equal to phi of y for xy in G, because phi is a mapping from G to G bar. Phi is a mapping from G to G bar. So you consider for any x and y in G, your phi of x and phi of y in G bar. So it is in G bar. So for 1 to 1 you have to consider two elements in the codomain to be the same, and you have to show that the pre-images, namely x and y in G, to be equal. So this is our aim. So for that only we have considered phi of x to be equal to phi of y, and post multiply both sides by phi of y the whole inverse. This is what you get. E bar being the, see, all these are elements in G bar. So when you post multiply, you'll have to write only the identity element which is present in G bar. So you get E bar here, and by the one of the properties of homomorphism, you can write phi of I the whole inverse to be phi of Y inverse. So this is because phi is a homomorphism. The previous one is post multiplying both sides by phi y inverse. So you get that step. And for the second one, the step, you have phi to be a homomorphism. Again, phi is a homomorphism, and that is why you are getting phi of x into phi of y inverse to be phi of xy inverse equal to E bar. That remains as such. Now kernel means it is all those elements which are taken to identity element, and this element being taken to identity element of the codomain by phi, this xy inverse should be there in kernel phi, and that is nothing but identity element. That's our assumption. So xy inverse can only be E, because kernel phi is E here, singleton E. So that in turn gives x equals y. So the images equal implies the pre-images are equal, and therefore we conclude that phi is 1 to 1. Now for the converse part, we shall assume that phi to be 1 to 1, then we'll prove that kernel phi is singleton E. So not to have just one element alone present in kernel phi, we'll have to consider y to be an arbitrary element in kernel phi. So as y belongs to kernel phi, we have phi of y to be equal to, because kernel phi is all those elements which are taken to identity element. So you have this. But our phi is a homomorphism, and therefore I can rewrite this E bar as the image of E under phi. So this is because phi is a homomorphism. And so phi of y equals phi of E. Images are equal because phi is 1 to 1. The pre-images, namely y and E, they must be equal. So you have y considered to be an arbitrary element. This is any arbitrary element in kernel phi, and that is nothing but E. So we conclude that kernel phi is singleton E. So we have established both the parts. Given phi homomorphism, we want to have phi to be an isomorphism, means we'll have to prove that kernel phi is singleton E, and whenever kernel phi is singleton E, if phi is a homomorphism, naturally it will be 1 to 1. Now fundamental theorem on homomorphism or first isomorphism states that if phi is a homomorphism of G onto G bar with kernel K, then G mod K is isomorphic to G bar. Phi is a mapping from G to G bar that is given to be onto homomorphism. This phi is given to be onto homomorphism. with kernel K. With kernel, any homomorphism will have kernel. So this homomorphism has kernel, that is taken as K. If this is the case, then this theorem says that G mod K is isomorphic to G bar. So to establish that, we will be considering a mapping psi between these two and show that that mapping is well defined. First we define the rule and show that that is well defined, one-to-one, onto, and homomorphism. So what is given? First we write let phi from G to G bar be the given onto homomorphism with kernel K. K means the kernel, so all those elements which are mapped onto the identity element of the codomain. That is named as equation 1. Now we already know that kernel of a homomorphism is a normal subgroup of G. So K is normal in G. So G mod K is defined and it exists as a group, quotient group. So if we have to discuss homomorphism between two structures, they should be of the same nature. That is, group means group, like that. So for that only we ensure here whether G mod K is a group or not. Because K is normal, G mod K exists as quotient group. So we are justified in defining our psi to be a rule from G mod K to G bar, and that rule is given by psi of Kg equal to phi of G. Already phi is a mapping from G to G bar. So already phi is a mapping from G to G bar. Phi is a mapping from G to G bar. So when we consider G in G, this phi of G will be in G bar. So we are justified in considering this mapping, this rule psi from this to this in this way. Now being defined wise, we have to show that this is well defined. Only then we can call that as a mapping. So we consider in the domain, we have in the domain G mod K, and in the codomain we have G bar. So we consider two elements in the domain, Kg equals Kg prime, where G prime are in G, G and G prime are in G. So we consider two elements in the domain to be the same, and because we know already that HA equals HB if and only if AB inverse belongs to H. This is already discussed in section 2.4. So G prime inverse belongs to K, but K is nothing but kernel. So by equation 1, that is the definition of K, this element's image under phi should be the identity element of the codomain. So we have this because phi is a homomorphism. This can be rewritten in this way, and this is of the form AB inverse equals E means A equals B. So based on that, you have this one to be phi of G equals phi of G prime. But phi of G is nothing but by 2, it is nothing but that is how it is defined. The rule is defined that way. So you have phi of G to be psi of Kg and this one to be psi of Kg prime. So we started with Kg and Kg prime to be equal in the domain, and we have got the images to be the same. So for well defined, from the domain you have to go to the codomain. But for the one-to-one part, from the codomain you will have to come to your domain. So it should be the other way around. It should be the other way around for one-to-one. And for this well defined, from here to there you'll have to go. So next our target is to show that psi is 1-to-1. The first one tells us psi is well defined. Now psi is 1-to-1. So for psi to be 1-to-1, we have to assume the images to be equal. So psi of Kg is the image of Kg under psi. So it is assumed to be the same. Psi of Kg equals psi of Kg prime. Now that in turn gives, because by the definition here using 2, you have this to be phi of G equals phi of G prime. And post multiplying both sides by phi of G prime, the whole inverse, here you have identity element in G bar. All these are taking place in G bar. So identity element in G bar being E bar, we'll have to write E bar here. And because phi is a homomorphism, you have this step. And all those elements which are taken to identity element by phi, should be there in kernel. So you have G prime inverse to be in K. And again, we make use of the same concept that HA equals HB for only if AB inverse belongs to H. We have, again, this is done in section 2.4. So Kg equals Kg prime. The pre-images are equal. We assume the images to be the same and we have got pre-images to be equal. So your psi is 1 to 1. Now we prove that psi is onto. So for that we'll have to assume we have G by G mod K to be the domain and G bar to be the codomain. This is for psi. This is for psi. But for phi is a onto homomorphism from G to G bar. So for both of these two functions, namely phi and psi, G bar is the codomain. So for psi to be onto, I will have to consider an element G bar in G bar. But already having got our phi, which is onto, for this G bar, there should be one G here. From here to here, we'll have to come for onto or even for 1 to 1. So for any G bar in G bar, because phi is onto, we'll have to have an element G as pre-image such that phi of G is equal to G bar. But phi of G, once I have G, I can talk about Kg present in G by G mod K. So you have this phi of G by 2 to be psi of Kg. So for every G bar in G bar, there exists one Kg in G mod K such that G bar is psi of Kg. So this shows that psi is onto. We have got psi to be onto. So psi is onto because we are given phi to be onto. Next, we have to show that psi is a homomorphism. So to prove that psi is a homomorphism, we have to say that the operation is preserved. So in that is psi of Kg dot Kg prime is psi of Kg dot psi of Kg prime. So we consider LHS. So to prove homomorphism, what is to be proved is to be written first, and then in that you consider the LHS and try to establish that is RHS. So LHS is nothing but this. Because K is normal, K being kernel, it is normal in G. So K is normal in G. So that lets us to consider on this Kg prime. That lets us to consider Kg prime as Kgg prime. Kgg prime. And this one by the definition of psi, so this is by 2, how our psi is defined. So using 2. So you have this, because phi is a homomorphism, you have this phi of G. Because phi is a homomorphism, you have, already we are given phi to be a homomorphism. So phi of G prime can be written as phi of G into phi of G prime. But phi of G by 2 is nothing but psi of Kg into psi of Kg prime. So that is our RHS. So we have psi to be 1 to 1 onto homomorphism, and therefore by the definition of isomorphic groups, we conclude that G mod K is isomorphic to G bar. So what all that we have done, we'll have to define first what is the mapping from where to where that we are going. And even before to that, to start with, what is given first, that has to be written. Phi from G to G bar is onto homomorphism with kernel K. What is K? All these are to be written first, and then only it will be easy for us to proceed further. So in the next video, we will see this lemma alone in the next video, which is if phi is homomorphism of G onto G bar with kernel K. For H bar in G bar, we have H being defined in this way to be a subgroup, and K, the kernel, is contained in H. And if H bar is normal in G bar, then H is normal in G. And homomorphic image of a normal subgroup of a group G is normal subgroup of G bar. And this association, that is, I have the set of all groups of G bar and the set of all subgroups of G which contain K. We are going to establish a one-to-one onto mapping between those two collection. So that we will have in the next video. Thank you.